In this session, I'll be explaining the introduction part of computational fluid dynamics. First, we shall see what is computational fluid dynamics. The physical properties of any fluid flow are governed by three fundamental principles. They are mass is conserved, Newton's second law, energy is conserved. These principles are represented in the form of basic mathematical equations, either integral equations or partial differential equations. Computational fluid dynamics is method of solving these integrals or partial differential equations in simple algebraic forms, which are further solved to obtain the flow field values at discrete points in time or space. The output of computational fluid dynamics is a numerical solution different from analytical solution. Next, we have disciplines within computational fluid dynamics. Fluid mechanics deals with the study of fluids in motion or at rest. Particularly, computational fluid dynamics deals with fluids that are in motion, fluid flow behavior influencing processes that may include heat transfer and chemical reactions in combusting flows. This directly concludes to fluid dynamics. Usually, the physical characteristics of fluid motion are represented by fundamental mathematical equations, usually partial differential equations, which govern the processes and are known as governing equations in computational fluid dynamics. These mathematical equations are converted into computer programs or software packages by computer scientists by using high-level computer programming languages. The computational part deals with the study of fluid flow through numerical simulations in order to obtain numerical solutions. Next, we have need for computational fluid dynamics. The governing equations for fluid form nonlinear partial differential equations, which are impossible to solve analytically for most of the engineering problems. But it is possible to obtain approximate computer-based solutions for these governing equations, which leads to the need of computational fluid dynamics. Computational fluid dynamics is used in various automobile, aerospace, biomedical, chemical, civil, environmental, power, and sports industries. Computational fluid dynamics is more cost-effective, saves time compared to physical testing. The strategy of computational fluid dynamics. Computational fluid dynamics replaces continuous problem domain into discrete domain using grid. In continuous domain, as shown in the above figure, each flow variable is defined at every point in the domain. For an example, consider pressure P in a continuous one-dimensional domain, which can be given as P is equals to P of x, where x lies between 0 to 1. In discrete domain, the domain is divided into small parts. Those small parts are nothing but grids. Each flow variable is defined only at grid points in discrete domain. Therefore, in discrete domain, the pressure would be defined only at n grid points. The equation will be Pi is equals to P of xi, where I is equals to 1, 2, 3 up to n. The figure on the slide shows grid generation over an airfoil. Discrete system is defined as large set of coupled algebraic equations in discrete variables. Considering discrete system and solving it includes large number of repetitive calculations which can be solved by using digital computers. This idea of solving the problems can be applied to any problem domain. With this, I will end up this session here. In the next session, I'll be explaining the steps involved in computational fluid dynamics analysis. Thank you.